Science Beetle.
Hey, welcome back, students. What I want to do is kind of pick up where we left off last time. And last time we talked about chemistry, provided a very brief definition of what it was, said that chemistry is a study of what things are made of. And I provided you with a little bit of a deciphering of the word things, and said that things were the objects in our real world. And I also provided a little bit of a decipher on the words made up of. And what I meant by that was essentially that these objects in the real world are composed of smaller parts. And I called these objects in the real world, called them matter. At least that's the way they're referred to in chemistry. And so what I wanted to do today is to kind of build upon that and explain a little bit more about what this matter is. And so essentially what I want you to do at the end of this lesson is to understand that matter is no different than the objects in our real world. And I'm going to go ahead and explain how they're, why they should be viewed the same. Okay, so what I want to do with first is kind of give you a brief definition of what matter is and build from there. So matter is anything that has mass and takes up space. And so let me explain what this means here. I guess put it into a little bit plainer English. What do we mean by has mass? Well, many of you have already come across mass almost in your everyday life, and at one point or another someone has talked to you about mass, but they haven't called it mass. They've used another word for it. And so mass essentially is a gravitational force acting on you. And so what this really is, visually, if I could provide this as an example, say we have the Earth here, and I'm going to go ahead and kind of just label this so we know what it is. Essentially, when we talk about mass, we're talking about the force that gravity would exert on you as it attracts you closer to the Earth. And so essentially what's going on here is if I were to take you, this drawing is not to scale, but if I were to take you and just ask you right now, how much force is being pulled on you? Well, it's kind of negligible because we're always with this, but it's the force that kind of keeps you attached or on the ground, as opposed to floating up in the air without any kind of support. And so this gravitational force, the Earth is always pulling you down at a certain amount. And this amount, or this gravitational force, we usually say that this force, we usually call this in general as gravity. But what we're really talking about when we talk about mass is we're talking about how much weight is associated with the individual. So for example, this individual here that I've drawn, if the individual is a tall individual, that person is going to be probably heavier, if we consider the concept of weight, is probably going to be heavier than someone who is smaller. And so if I were to draw that in terms of here as opposed to, and then maybe a smaller person next to him or her, let's say that the force here is sizable, you know, with this individual here, but it's only that much with this individual here, and the arrows representing the amount of force being applied to the individual. Okay, so essentially what I'm saying is that the amount of gravity or the weight associated with an object or a person, which essentially is an object, is going to be greater as the object gets bigger, and it's going to get smaller as the object gets smaller, at least in general trend. Another way of looking at this is going to be the following way. Let's pretend that we have three organisms here. For example, we have an ant, which is right here, and we have you, which is right here, and then we've got the elephant at the very far right here. And let's say that we're asking ourselves, how much does each of these organisms weigh relative to one another? Well, in comparison, if I were to take the weight of the ant is going to be very tiny, okay? Almost insignificant, almost unnoticeable. And then if we take the weight of the human, you know, probably anywhere between 100 pounds and maybe 150, 180 pounds, right? But if we take the weight of the elephant, we're probably looking at several hundred, several thousand pounds now. And so the difference in weight is going to be huge. And one thing that you can look at, and kind of follows that principle that I was talking about, the size of the elephant is relatively big. So you look at the size of the elephant, essentially from here all the way over here. So you've got this entire size, right? And then relative to the human essentially is this. And so here's the relative size of the human, and then you've got the relative size of the ant, which is very tiny. And so what we can see here, as size increases, so does the weight associated with the particular object. Okay? And all we're saying here is that the weight is essentially the mass. So as the size of the object increases, the mass associated with that object is also going to increase. So based on our definition of matter, an elephant has mass because it has a certain amount of weight. So does the human. It has a certain amount of weight. And even though we can't, the weight of the ant is very, very small, it still does have a particular weight associated with it. So each of these examples then would meet the first condition of what matter is, that it has mass. Now let's look at the second one, the takes up space part. Well, if we were to look at these here, almost the same way, we almost can tell right away that the ant, the space for the ant is essentially very, very tiny compared to the amount of size that a human would take up and the amount of size that the elephant would take up. But instead of looking at it in this particular way, let me show you a different kind of diagram to explain kind of what I mean by size. So we've got this box, okay, essentially a grid. And in this grid, I've got 8 spots. So here's 1, 2, 3, 4, 5, 6, 7, 8 spots. Okay, so let me just write that here. We've got 8 slots. And so essentially what I want to do is I kind of want to show the differences in terms of the size of each of these 3 objects here, or these 3 organisms, and kind of explain what takes up space is. So if I were to take the ant and I were to put it in here in the first box, essentially what we would see is that the ant takes up that much space. It's a very tiny amount. So the first thing that you can see is that you could put a lot of ants in this container here, you know, and you can fill it up tightly, and essentially you can have a lot of ants in there, right? Well, let's just say that this number here, let's say that you're able to fit 100 ants in this container here, okay? Now, if we take the human, for example, if we take the human and input the human in the second box, how many humans will fit? Well, based on the relative size, we can probably just put the 1. They're roughly about the same size, okay? So we know now that the amount of space that's taken up by the ant is very small compared to the amount of space taken up by the human. Because in the first box, we were only able to fit 100. But when we compared that to the space for the human, we were only able to fit 1 human in the same space taken up by the ants. So we could fit more ants in the same amount of space than we could humans in the same amount of space. Now, if we were to take the elephant, for example, let's say we take this big elephant over here and we try to put it in one of these, is the elephant going to fit? The answer is no, it's not going to fit. And the reason it's not going to fit is because the elephant is too big. Okay? It takes up too much space. So in showing this little brief example or this brief diagram, what I'm trying to illustrate to you is that depending on the size or depending on the amount of area taken up by this object, then it's going to dictate how much space it takes. And we just saw that the bigger the object, the more space it's going to take, and also the more mass that it's going to have associated with it. And in all 3 cases, the elephant, the human, and the ant, they both took up space and they all had mass, essentially meeting the definition for what matter is. And so just like objects in the real world have mass and take up space, those same objects are also called matter in chemistry, and they have mass and they take up space. And so that's really what I wanted to cover today, to explain to you this concept of matter before we go any further. And in the next couple of lessons, we'll go a little bit deeper and explain a little bit more about matter and what its components are going to be.